Namaskar everyone. Today we will understand elastic methods of analysis. There are basically two basic methods for elastic analysis. One is called the force method and the other is called the displacement method. We have already discussed these methods in earlier chapters also. We are going to do these methods again. And this time we would be applying these methods to relatively more complex systems. So let us try to understand the force method using this beam, which is available on your screen, figure 13.1. So we have a beam in front of us, and the reactions are RA, RB, RC, and the external load is capital P1 and capital P2. Now this is a indeterminate system. This system would become statically determinate if we remove reaction RB. So in the force method, what we do, first of all, we make the indeterminate system statically determinate by removing certain reactions. So now look at figure 13.1b, and we can see here the reaction RB has been removed. And triangle BP is the deflection at point B due to the forces capital P1 and capital P2. Next, what we do is we remove the external loads capital P1 and capital P2 as in figure C and apply the reaction RB. And in this case, let us call it capital XB. And now we try to find out triangle BB, which is the deflection at point B due to application of load RB at point B. After this, we argue that delta triangle BP plus triangle BB should be equal to 0. This we do because, as we see in figure A, there can be no deflection at point B. So triangle BP plus triangle BB should be equal to 0. And from this relation, we can find out the reaction RB. So to again recall this method, in force method, first of all, we reduce the indeterminate system into a statically determinate system by removing redundant reactions. Then we find out the deflection at the points where reactions have been removed. Thereafter, we remove all the external loads and apply the reaction which was previously removed and find out the deflection. And thereafter, we apply the boundary conditions, compatibility boundary condition. And this application of compatibility boundary condition gives us another equation to us, which helps us in finding out the reactions, which were initially indeterminate. Now, to understand more, let us now look at figure 13.2. In figure A, we can see we have vertical reactions RA, RB, RC, RD, and external load capital P1, capital P2, capital P3, and a distributed load capital W. This is indeterminate system. This indeterminate system, which is shown in figure A, would become determinate if we remove reactions RA and RC. So we have removed reactions RA and RC, and this becomes a statically determinate system. And then using our deflection equation, we can find out triangle BP, which is deflection at point B due to the external loads P. And we can also find out triangle CP, which is deflection at point C due to the external loads. Now let us look at figure C. In figure C, we have removed all the external loads like capital P1, capital P2, capital P3, and the distributed load capital W. And we are applying the reaction RB. Now this is statically determinate system, and we can find out triangle BB, which is deflection at point B due to load RB at point B. And we can also find out triangle CB, which is deflection at point C due to load RB equal to XB at point B. Next, look at figure D. Here also there is no external load which is acting, and we have applied load RC equal to capital XC at point C. And this is a statically determinate system. And using the deflection equation, we can find out triangle CC. And also we can find out triangle BC, where triangle CC is deflection at point C due to application of load RC equal to XC at point C. And triangle BC is deflection at point B due to application of load RC equal to XC at point C. Now let us look at figure E and F. Now in figures E and F, we have defined flexibility coefficients FBB, FCB. FBB is flexibility coefficient, which means deflection at point B due to unit load at point B. And FCB is deflection at point C due to unit load at point B. And similarly, we can see figure F, where FBC is deflection at point B due to unit load at point C, and FCC is deflection at point C due to unit load at point C. Now, we can now, after doing all this, now we have to apply the compatibility condition. Compatibility condition demands that triangle BP plus triangle BB plus triangle BC should be equal to 0, because there cannot be any deflection at location of point B. And compatibility condition gives us one more equation, which is from figure B, triangle CP, from figure C plus triangle CB, and from figure D plus triangle CC should be equal to 0. That is triangle CP plus triangle CB plus triangle CC equal to 0. So these two equations are here, which we have written in form of equation 13.1. So here we have in front of us equation 13.1, triangle BP plus triangle BB plus triangle BC equal to 0, and triangle CP plus triangle CB plus triangle CC equal to 0. Usage of these two equations allows us now to find out the reactions at point B and point C. Now here, let us define flexibility coefficient. Flexibility coefficients FBB and FBC, they are defined as in equation 13.2, where we can see triangle BB equal to FBB capital XB and triangle BC equal to FBC into XC, where FBB is deflection at point B due to unit load at point B, and FBC is deflection at point B due to unit load at point C. FCB is deflection at C due to unit load at point B, and FCC is deflection at C due to unit load at C. So here we can see that how we can express triangle BB, triangle BC, triangle CB, triangle CC in terms of flexibility coefficients FBB, FBC, FCB, and FCC respectively. And this gives us now the compatibility equations in terms of flexibility coefficients, and which is FBB capital XB plus FBC capital XC plus triangle BP equal to 0, and FCB capital XB plus FCC capital XC plus triangle CP equal to 0. And in these two equations, the unknowns are XB and XC. There are two equations, two unknowns, so XB and XC can be found out easily by substitution method. Now, generalizing the above results for determining the unknown forces for systems when n redundants, the following compatibility equations can be formed. So, triangle A equal to FAA XA plus FAB XB plus like that FAN XN plus triangle AP. So this way we can find out the compatibility equations, and these equations can then be written in matrix form as in equation 13.136. And then this matrix system, this matrix equation 13.6 can be solved for the vector capital XA, XB up to XN. Now let us look at the flexibility coefficients reciprocity. Now, displacement triangle I at I due to forces Pi at I and Pj at J can be written as triangle I equal to Fii Pi plus Fij Pj, where Fii is flexibility coefficient, which means deflection at I due to unit load at I, and Fij is also flexibility coefficient, which means deflection at I due to unit load at J. Similarly, triangle J can be written as Fji Pi plus Fjj Pj. Now, using Castigliano's second theorem, we can write that triangle I is equal to curly capital U by curly Pi, and triangle J is equal to curly U by curly Pj, where capital U is the strain energy of the system Okay. Now let us and also we can see, if we take derivate this curly triangle I by curly pj, we can write fij, and that becomes curly square u by curly pi curly pj curly pi. And similarly, curly triangle j by curly pi, that becomes fji, and that is curly square u by curly pi into curly square u by curly pi curly pj. Now, since the order of differentiation is immaterial, so we can write that fij is equal to fji, right? That means deflection at point I due to unit load at j is equal to deflection at point j due to unit load at point I. So let us look at this cantilever and try to understand reciprocal deflections Fij and Fji. So in figure A, we can see there is a unit load which is acting at jth point at the cantilevered end. And uh, and at x equal to A, we can see we have Fij, right? Which means deflection at I due to unit load at J. And if you look at figure B, we have a unit load at I now. So this unit load at I gives Fji at the end, which means deflection at J due to unit load at I. So this theorem of reciprocity of flexibility coefficients, that means that Fij has to be equal to Fji, and this we can visualize from this particular example of a cantilevered beam. Now let us look at this example. For the simply supported elastic beam shown in figure 13.4, show that the rotation of the tangent to the elastic curve at the support I caused by applying a unit force at J is equal to the deflection at J caused by applying a unit couple at I, right? So rotation of the tangent to the elastic curve at the support I caused by applying a unit force at J is equal to the deflection at J caused by applying a unit couple at I. So let us see how we can do that. So here we have a simply supported beam, and at location J, we are applying a vertical unit load, and we have to find how much is the slope due to this vertical unit load at J. We have to find how much is the slope at end I. So for this, we know that the deflection expression is given by V equal to minus PB by 6 EIL bracket start L square X minus B square X minus X cube bracket close. If we differentiate it, we get V dash equal to minus PB by 6 EIL bracket start L square minus B square minus 3X square bracket close. And where A and B have the meanings as depicted in this figure. And V dash at X equal to 0, we can compute, and we find that it comes out to minus PAB by 6 EIL bracket start A plus 2B bracket close. Now, Fij or theta ij would become AB by 6 EIL bracket start A plus 2B. Now, if we consider the second figure, here a unit moment is applied at end I. And we have to find out that how much would be deflection at point J due to application of unit moment at end I. So for that, again, let us write the expression of bending moment, which we can write as capital M equal to minus m naught plus m naught x divided by L, and EI V double dash equal to minus m naught plus m naught x by L. So integrate it and we get the expression of V, and we can see that this Fji that comes out to be equal to AB divided by 6 EIL bracket start A plus 2B bracket close. So this result is identical to what we had derived in equation 13.8. Now we have another example in front of us. So this is a two-span continuous elastic beam on simple supports, carries a uniformly distributed load as shown in figure 13.5. We have to determine the reactions and plot shear and bending moment diagrams. EI for the beam is constant. So this is the beam, and this beam is experiencing reactions RA, RB, and RC. So in this beam, first of all, we will remove the reaction RB, and this system would become statically determinate, and we will find triangle BP. Thereafter, we will remove all the loads, external loads, and apply unit force at location B, and we will find out FBB. So that, and then we will use the compatibility equations. That's all. So triangle BP can be found out as equal to minus F naught minus 5 W naught L4 divided by 24 EI, and FBB can be found out as L cube by 6 EI. And then, since the supports are immovable, so triangle B has to be equal to 0. That means FBB XB plus triangle BP equal to 0, and that gives us the reaction XB equal to 5 W naught capital L divided by 4. Now let us look at this example. Now in this example, we can see that this example is indeterminate to the second order. So that means there are two reactions which are redundant. We have to remove two reactions. So here we are seeing that there is a beam which is experiencing a uniformly distributed load, and the reactions are at 3 points RA, RB, and RC, and there is also a reaction of bending moment MA. To make it statically determinate, we will remove RB and also we will remove MA. Once RB and MA is removed, then by using the deflection equation, we can very easily find out value of triangle BP, which is deflection at point B due to the external loads, and triangle AP, that is again slope at end A due to the external load W naught. Thereafter, what we will do is, as in figure C, we will introduce the reaction of 1 Newton at point B. Again, this system is statically determinate, and please see there is no external load which is acting here. Now we will not consider the external loads, and we will find out FBB and also FAB. FAB is slope at A due to unit load at B, and FBB is deflection at B due to unit load at B. And in figure D, we will find out FBA and FAA when we apply unit moment at end A. So we have applied unit moment at end A, and FBA is deflection at B due to unit moment at A, and FAA is slope at A due to unit moment at A. And then we will use the compatibility equation. So we have found out triangle AP, that is minus W naught L cube by 3 EI, triangle BP equal to minus 5 W naught L4 by 24 EI. And then we have also found out the flexibility coefficients FAB, FBB, FAA, FBA. And now at the end of the page are the compatibility of displacements at A and B, which gives us triangle AP plus FAA XA plus FAB XB equal to 0, and triangle BP plus FBA XA plus FBB XB equal to 0. In these two compatibility equations, only unknowns are XA and XB, and which can be easily found out by mutual substitution in these two equations. And we can then finally find out the values of XA as 0.0714 W naught L square and XB equal to 1.143 W naught